Welcome to part 3 of this week's online lecture. In part 3 we will discuss the symmetries of vibrational states. In the next few slides I want to discuss the symmetries of vibrational wave functions. We want to look at the symmetries of the vibrational states in order to determine the selection rules for infrared spectroscopy. We will be considering the vibrations of water, which belongs to the C2V point group, and so we will be determining which water vibrations are infrared active. We can start by looking at the vibrational ground state. In any mode, the ground vibrational state has this type of wave function. It is a Gaussian function. That is, it is proportional to the exponential of the square of the normal mode coordinate. Note that in terms of the lowercase q that we used in part 2 to describe the vibrations of water, the uppercase q is simply a mass-weighted coordinate. It is formed from the product of the lowercase q times the square root of the reduced mass. If we apply any symmetry operator to this function, then q may change sign. For instance, if it is qa, the mass-weighted normal mode for the asymmetric stretch. But q squared is always unchanged. Therefore, the ground vibrational wave function psi0, 0 because it is the v equals 0 vibrational state, is always symmetric. It always has symmetry A1 in the C2V point group, no matter which vibrational mode we are talking about, whether the symmetric stretch, the asymmetric stretch, or the bending mode. Now let's look at the excited vibrational states. The first two excited vibrational states have the following mathematical form. Note that psi1, the first excited vibrational wave function, is the product of q and the ground state wave function, and psi2, the second excited vibrational wave function, is the sum of the product of q squared and the ground state wave function and the ground state wave function. For the asymmetric stretch qa, which has symmetry B2, psi1 is the product of q, which has B2 symmetry, and psi0, which has A1 symmetry. Thus psi1 for the asymmetric stretch has B2 symmetry overall. That is because the product of the irreducible representations B2 and A1 is equal to B2. The next vibrational state, psi2, for the asymmetric stretch, has A1 symmetry like the ground state. In fact, psi sub v for the asymmetric stretch has B2 symmetry if v is odd, i.e. if it's in the 1, 3, 5 vibrational state, and A1 symmetry if v is even, i.e. if it is in the 0, 2, 4 vibrational state. The bend and the symmetric stretch both have A1 symmetry, and since A1 times A1 is equal to A1, all of their states have A1 symmetry. So how does identifying the symmetries of the vibrational states help us identify the selection rules? Well, remember that the intensity of a transition is proportional to the square of the transition moment. By definition, an integral is just a number, so symmetry operations have no effect on it. However, the integrand may be affected by symmetry operators, and if there is any symmetry operator that changes its sign, it will change the sign of the whole integral. There is a contradiction unless the integral is 0. Therefore, the integrand must have overall A1 symmetry for it to be non-zero. This is because only an integrand that is totally symmetric is unchanged by the effect of any symmetry operator. Accordingly, the integrand must be symmetric, A1 in the C2V point group, for the integral not to vanish, because symmetry operators leave functions with A1 symmetry unchanged. The dipole moment mu can be broken down into three Cartesian components: mu x, mu y, and mu z. For instance, mu x is simply the sum of the charges times the x-coordinate of the charges. Thus mu x, being the sum of the x-coordinates, which all have B1 symmetry, has B1 symmetry. Similarly, mu y behaves like y, that is, it has B2 symmetry, and mu z like z, that is, it has A1 symmetry. The vibrational states in water have symmetries that are either A1 or B2. We can therefore construct the possible symmetries of the integrand of the transition moment. The first column in this table indicates the dipole moment component mu x, mu y, and mu z. The second column indicates all the possible symmetries of the initial and final vibrational states, either A1 or B2. The third column indicates the symmetries of the elements in the integrand, that is, the symmetry of the final wave function times the symmetry of the dipole moment component times the symmetry of the initial wave function. Determining this triple product of symmetries is simply a matter of determining the character under each of the symmetry operators by multiplying together the characters of the three irreducible representations together. If the irreducible representations are non-degenerate, then this product will lead to a non-degenerate irreducible representation that can be immediately identified from the character table. And if the integrand has overall A1 symmetry, then the transition is allowed, else it is forbidden, and this is identified in column 4. So no transitions are possible if the polarization is in the x direction, that is, perpendicular to the molecular plane. Transitions between A1 and B2 are allowed if the polarization is in the y direction, and transitions between A1 and A1 or between B2 and B2 are allowed if the polarization is in the z direction. The most important result of the foregoing discussion is given by the following note. In general, we find that infrared transitions can occur if the symmetry of the vibration is the same as the symmetry of some component of the dipole operator. That is, if the vibration transforms like x, y, or z. This is the end of part 3 of this week's online lecture. Please continue on to part 4.